I just thought that the last speaker is very important because he finished early, then everybody happy. Okay, today I brought something very elementary and something very simple. And okay, the equation is to want to talk about the Burger's equation, but the focus is the asymptotic agreement of a moment will give some contraction, higher contraction orders. And in this is also I consider the asymptotic convergence and moment. And inside there is some asymptotic scale, and that we are going to see how they play together and give a higher order contraction order. So that's the story of this talk. And this talk is a joint work with my graduate students, YongJung and Eugenia Kim. And the goal of this study, okay, I already talked about this one. And then the outline first, okay, consider heat equation first. And we already saw a lot of things from heat equation. And then to see how to control the moment for the heat equation. And then consider Burger's equation. And how to control moments for the solutions of the Burger's equation. Then, okay, for the more general case, how to obtain fine asymptotics and how the asymptotic scale is related to this fine asymptotics. And in many of the talks, somehow many people could, actually I saw at least 2 or 3 talks that mention something related to this kind of thing. Okay, so the heat equation, okay, it is just the heat equation. Now, what is the moment? Moment is just this thing. So we say for any given t, okay, so then at that moment, this is the moment, kth order moment of the solution. And if you differentiate this one, you can easily check that derivative of the kth moment is given by this. Okay, so kth order moment is given by its initial one, and then the lower order moment. So if you sum them up, then you can easily compute this kind of relation. So at any time t, you can easily compute kth order or any order moment given in this relation. And if you think just this, then since the heat equation is not reversible, you may think that this one is defined only for t bigger than 0, but that is not true. If you consider just this relation, putting negative numbers to t, okay, you still have the moment. And we want to call that a backward moment in time. So basically the moment is defined for any time using this relation, even though there is no solution. Oh, there's one more thing. And what I mean, this also says that if you have, so moment at any time t is completely decided by the initial moment. Okay? So that means if V is another solution and this one satisfies this relation, that means if V has the initially same moment as the first solution U, then we can say that the moments are always the same for all time t. And this kind of agreement of the moment is a special property of the heat equation only. And using this relation, you can easily check that these two solutions, if the moments agree up to 2n-1th order, then they are contract having this order. So there's a very higher order contraction. Then, okay, if you, so basically you set the n number of moments, then you have this high order contraction, and here square root of t appears. And why we have square root of t? You can think that everybody knows that in this one-dimensional heat equation, the similarity variable is this one. And this similar, or if you see the heat column, this thing appears here. And you can see that the solution is expanding in time with the scale of square root of t. So we may say that this square root of t is the asymptotic scale of the solution of this heat equation. And that one appears exactly here. Next. Up. Okay, so here, so if you want to construct, for example, an approximation or construct another solution that shares the same moment, then how to make it? So to find another solution that has exactly the same moment of the certain order, one easy way is this one, and this method is very well known. So for example, if you consider when t equals 0, then so this phi is a heat kernel as we have here, and so phi is a heat kernel always in this term. Then when t equals 0, this one is actually Dirac measure, and derivative of Dirac measure is the initial value of this one. And if we want to check the moment of this one, just use the integration by part for the distribution sense, then you can easily check that moment of this one is exactly the moment. Case of the moment of this one is exactly that. So this is very easy way to set the moment. And if you want to see V is an approximation of the original solution U, then for large t, this is a very nice approximation. But for small t, this is not so good because you do the differentiation for that Dirac measure, then it becomes worse and worse and worse. So this one is good for t large only. And okay, so then if you don't like to do the differentiation, okay, let's try to find another way to set the moment in this way. So definitely this one is also a solution of a heat equation. Now here's rho I Ci I want, and then if you put the 0 here, then the initial corresponding initial value is this. Now compute the moment of this one. The moment of this one is just this. Okay, so I want to. So here I have two n freedom of choices for rho i's and ci's, and use them to satisfy this relation. And is that possible? The answer is yes, if your initial value is positive. And the theory is exactly the truncated moment problem theory. So it's not actually in our group. It's the problem of our group, but we have a bunch of people somewhere who do this kind of moment problem. Okay, and this truncated moment problem is good for positive initial value. Okay, then at least if the positive, then we can solve this one, and then we can construct this kind of approximation, and this kind of higher order approximation.
Can you do the opposite initial data for the positive part and play this rule, negative part play this rule? Is this okay?
We can do that, but some I feel like that is not the optimal way. Okay. Yeah. So that yeah. Another, but there is still. Okay. So this one is better than the previous one because we do not differentiation. But still, when t equals 0, this one is a series of delta functions, and that is still bad. This one has no regularity at all. So okay, then let's try one more thing. Then our third method to control moments is, okay, approximate this one with this for some positive t naught. Then now this one may have some regularity. Then the moment of v, not at t equals 0, but at t equals minus t naught is this one. Then to set the moment, now here backward moment appears, and try to solve this equation. Now, even if the initial value u0 is positive, then this is not exactly a moment of the positive value. So we are not even sure if we can solve this kind of equation. And if we can solve this, now there is one more freedom of choice, T naught, and use one extra freedom and set one more moment here. Then we can obtain this kind of a higher order contraction order. But we don't know how to solve this yet. But what we can do is, if T naught is fixed, then we can solve this, not in exactly this way, but we can set a moment up to 2n minus 1. How to do that? So not exactly, we don't have a solution of this one. We have a solution for this modified one. So we have developed a theory for the generalized complex moment problem. Okay, and then instead of the previous one, we can solve this one. We can find rho i's, c i's that satisfies this. Now rho i's, c i's are complex numbers. Then my approximation is something like this, and now phi is a heat column in the complex sense. Then we can make this. Okay, so somehow the generalized complex moment problem gives some better result, and we have this. Now, if people want to go to one further step, that instead of using T naught, we may consider Ti's for each of the summations, right? So probably this is the full potential. Now here we have a 3n freedom of choices, and use those things and to satisfy 3n equations. Is that possible? Okay, I have no answer. So for this kind of thing, I started to make some kind of discussion with Taku Yanagisawa in Nara Women's University. So we are trying to work on this one. Okay, so this is the way to set up the moment for the solutions of the heat equation. Now back to our original problem, the Burger's equation. Okay, Burger's equation is here. Now Burger's equation is a nonlinear problem. It's different. Now suppose so V is another solution that has initially the same moment of the certain order. Okay. Then for t bigger than 0, the moments are same. Answer no. This one holds only for k equals 0 only. So even if you set up the moment up to initial moment of the certain order, all you can get is just this. Right? Okay, so that's the bad thing. What's wrong? What you wanted to see is asymptotic behavior for t very large. So if you can set up the moment at t equal infinite, then probably you will get higher order contraction here. Then how to do that? That is the code of transformation. Okay, we know the code of transformation. Then somehow we can find rho i's. There is rho i's, CS complex numbers that the moment, kth order moment. It's not exactly a moment, but it's not exactly the difference of the kth order moment, but it's a norm in L1 sense. Then we can show that we can find rho I, Ci's that satisfies this higher order contraction. So for example, if you just to compare the solution, that means the zeroth order moment, when k equals 0, then you recover the same contraction order. Okay, so what is Wn? Wn is an inverse code of transformation of psi n. What's psi n? Psi n is integral over little psi n. What is little psi n? Psi n is the one we have constructed in the case of the heat equation. So here's rho I, Ci's. They are picked to satisfy the moment problem for the code of transformation. So let's fix the derivative of the code of transformation and set the moment of this one as alpha k and solve the moment problem here. And then construct psi n then take the inverse transformation, then this Wn is the one. Wn is the solution to the Burger's equation, which has the same moment of the original problem at t equal infinity, not t equal 0, at t equal infinity. Okay, so in this way, we can obtain the construction of some higher order contraction order. So somehow. Not now. It's just how many minutes? I still have plenty of time, right?
So you have 20 minutes.
20 minutes. So I'll try to.
Quite a non-linear, right? Cosine is linear superposition.
Yeah.
Wn is non-linear.
So yeah, this inverse Koolhof transformation is not linear. Now suppose we consider not the Burger's, so some other things. And for example, if you have the force medium equation thing, m bigger than 0, then we know that the Barenboim solution is play the role of the Gauss heat common in this problem. And this is C is the similarity variable given in this form. And this alpha is 1 over m plus 1. So this one says, wait a second, I have to also say that in the previous ones. Oops, I'm going backward. The theorem. So here, in this case, we still have square root of t, and the similarity variable of the Burger's equation is still x over square root of t. It's the same as the heat equation, so the same thing appears here. So Burger's case. So now, this case, force medium equation case, okay, this one is the similarity variable. Now the power is same when m equal 1. If m equal 1, that's the square root of t. But that's exactly the heat equation case. If m is not 1, this is the similarity scale variable is different. So in some sense, the way of the expanding the profile, the speed of the expansion of the profile is not square root of t, it's t to the alpha. This is a different order. If you consider the P Laplacian equation, something like this, we also saw this kind of equation today. Then the KC, the similarity scale is this, and this one with this power gives how the solution is expanding. So I want to call that asymptotic scale of the solution. Now, if your solution, if you are considering equation that plays many different things together, then you don't have a similarity variable. That's very clear. But this one still has some asymptotic scale, t to the alpha. And in this case, for example, 1 over q is the similarity, gives you the similarity scale for this convection. This one is for this PME type diffusion. This one is for the P Laplacian type diffusion. Now take the maximum of this one. Then that alpha is exactly the asymptotic scale of the solution of this problem. And if you rescale this one, if this one is the asymptotic scale, then if you rescale this, then this one preserves the L1 norm, and this one converges to non-zero L1 solution. So somehow the asymptotic scale means that this transformation converges to some non-zero L1 solution. So So you may consider this equation, or you may consider even more general case. But let's assume that there exists some asymptotic scale. Then what can we obtain? What kind of convergence order can we obtain if we set the moment up to a certain high order? So let U and V be two solutions. Okay, let E is the difference. Now, if the difference and nth moment, not exactly the nth moment, but L1 norm. So L1 norm of nth moment of something like the difference. If this one is order O1 for T large, then what can you do? Then I want to show that we can obtain the convergence order we observed in the previous cases. Okay, then, we want to, so alpha is the asymptotic scale. Now let's consider just any beta and do the change of variable and plug into this one. And want to show that if we can obtain this kind of estimate, so this is the nth order moment in some sense. If we can estimate this one with these two, then we can show we can obtain the contraction order. And if you want to expect this one, this alpha should be, this beta should be alpha. If beta is not alpha, it is not possible to obtain this. That's very clear. For example, beta is bigger than alpha, then you can easily see that. You can easily see that this part becomes a delta measure. So if you do this integration, you will get 0. So that means you cannot obtain this lower estimate.
Excuse me,
Yeah.
I see in 22 only beta, there's no alpha.
I picked arbitrary beta here.
Okay.
And the claim is that to make it sense, the only way is to choose beta equal alpha.
Oh, I see.
Okay, why the scale should be given by this asymptotic scale? That's what I'm explaining. So if, for example, if beta is bigger than alpha, okay, then this one is so alpha, if you so this one converges to some L1 if alpha is the asymptotic scale. And so if you can somehow see that if beta is bigger than alpha, then somehow this one this one becomes this one becomes something like a delta measure. So if you compute that, all you can expect is 0, so you cannot obtain this lower bound. And if beta is less than alpha, then it becomes somehow becomes flatter and flatter and flatter. So that means the roll of this one is bigger than for any constant c, so you cannot obtain the upper bound. So okay, so this one should be the only case. And my conclusion, so in various cases, if you can estimate this kind of thing with some alpha, then you can obtain contraction order. So I'm not saying, so for example, for the heat equation case, Berger's equation, we can do this. But for other cases, I'm not sure. We did not do that yet, but probably, if you can do that, then what can you do?
Oh, I see. Because the leading term has to, okay.
Yeah.
Otherwise, the low order term come to interfere.
So you can easily compute that and obtain the convergence order. So if you have the estimate, then there always exists C star, depending on T, between little c, capital C, that satisfies the relation. Then if you want to compute this one, then, okay, follow the step. Then that's order 1. That means this one is order 1 over T to the n alpha. Okay, somehow. So we have this one. So that's the fine asymptotics of this thing. So the reason why I did this, consider this kind of thing is many people asked me this kind of question. In the earlier work, we say if they have the same mass, then they contract with certain order. If you set the center of mass together, then it have many cases you have a higher contraction order. then people ask me, so what's the next level? At that time, I did not have any clue. But something like the moment, if you consider the moment asymptotically when t equals infinity. I don't know. In many cases, I don't know how to control that. For the KineticTheory case, I know how to control that. But for many other cases, if you know somehow if you find out a way to control the moment at t equals infinity, then you can obtain some higher order contraction order. And also, I remember that the Professor Weinberg in Minnesota, he suggested to me that, okay, if you consider, you did many things for t very large, t infinite, then what is the optimal thing when t are finite? So that kind of, so at least when t equals infinity, if we can do that, then we have this kind of convergence order. Finite time t, I think that's even tougher. Yeah, that's it. Thanks.
Any questions or comments? I have very nice questions, so